Okay, so I was asked by Ray to talk about disk-planet interactions. In fact, he was talking throughout his talk about disk-planet interactions as well. I'm going to restrict myself to talking about interactions via gravity that occur during the early stages of planet formation, and in particular about planet migration. There are two flavors of planet migration. Planet migration early in the history of the formation of the system, with the interactions with the gaseous protoplanetary disk, and later interactions with the planetesimals that are left over in the disk after the planet formation is partially complete and after the gas has been dissipated. The first of these to be recognized was planet migration induced by planetesimals. Let's see if this works. No, so I'll go this way. And that recognition dates back to a famous paper by Oort in 1950 on the formation of comets. Oort argued that the comets that we see come from a huge cloud of comets, tens of thousands of AU away from the sun, and that the planets were injected in planetesimals, that comets are really planetesimals, and the planetesimals were injected into the comet cloud by scattering from the giant planets in the outer solar system. The mass in the comet cloud is a few Earth masses. The efficiency of injecting comets into the comet cloud is only a few percent, so this already told you that there had been a substantial interaction between planetesimals and the giant planets. It was Safronoff in his seminal paper on formation of the solar system in the 1960s who recognized that if this process did occur, then by energy and angular momentum conservation, as you scattered planetesimals into the comet cloud, you correspondingly had to remove energy from the giant planets that were doing the scattering. And of course, the relation is simply that the ratio of the final semi-major axis to the initial semi-major axis of the planet is the ratio of the mass of the planet to the total of the mass of the planet on the ejected mass. And in fact, one of the major constraints on one of the emerging problems with understanding the comet cloud is that the mass that you have to eject is sufficiently large that it might have led to excessive migration of the planets. The first specific investigation of this process was by Fernandez and Ip in 1984 using rather crude numerical simulations, but one of the things they recognized is that although if you have a single planet that's ejecting planetesimals, it will always move inward. In the actual configuration of the giant planets that we now have, what typically happens is that Saturn, Uranus, and Neptune scatter planetesimals inward. Then Jupiter is such a strong scatterer that it kicks them out. It acts as a sink. So on the whole, these three planets are ejecting things inward and migrating out, whereas Jupiter is migrating in. And not surprisingly, since Jupiter's the most massive planet, it tends to migrate the least in their simulations, although these are very uncertain, migrated by a few percent inward, and the largest was Neptune, which went out by 20%. The paper that really turned this into that really confirmed that this process had occurred and made it a very interesting one was by Renu Malhotra in 1993, who pointed out that the outward migration of Neptune naturally explained several of the puzzling features of Pluto's orbit. And let me just say a little more about that, since it was such a important way of finding, in the sense that it rearranged our view of formation of the solar system. I'll call Pluto a planet, despite for brevity, despite what the IAU says. It has the most unusual orbit of any of the planets. Eccentricity is the largest, 0.25. Inclination is the largest, and in particular, its perihelion distance is slightly smaller than the semi-major axis of Neptune, which means that Pluto crosses Neptune's orbit every couple of hundred years. And the question naturally arises, how do they avoid colliding? It's had maybe 10 to the seventh crossings of Neptune's orbit since the formation of the solar system. and simple statistical mechanical arguments suggest that they should have collided long ago. The answer to that is that they're in resonance. The orbital period of Pluto is exactly 1.5 times the orbital period of Neptune. The particular flavor of resonance is precisely the one that I talked about yesterday. That is 3 times the mean longitude of Pluto minus twice the mean longitude of Neptune minus the longitude of periaps of Pluto librates around 180 degrees. And you can see that that means that when Pluto has crossed Neptune's orbit, that is when it's close to perihelion, this quantity and this are equal, and that says that the longitude of Pluto minus the longitude of Neptune is roughly 90 degrees. That is, the resonance ensures that Pluto always avoids Neptune when it crosses its orbit. And that can be seen in if you go to a reference, this is a reference frame that rotates with Neptune. It shows the orbits of Jupiter, Saturn, and Uranus, and this is the orbit of Pluto, and you can see that because of this resonant angle, Pluto's orbit slowly wobbles back and forth this way with a time scale of a few tens of thousands of years, but it always stays well clear of Neptune. This was discovered in one of the first numerical integrations of the solar system back in the 1960s, but what was completely unclear is how Pluto got into this strange orbit. And what Malhotra recognized is that if you believed Fernandez and Ip and Safronoff, so that Neptune was migrating outwards, all you had to do was imagine that Neptune went outward and Pluto was initially in a low eccentricity, low inclination orbit outside Neptune. As I argued yesterday, if the eccentricity is low enough and the migration is slow enough, it's inevitably captured into the 3-to-2 resonance. This is a result of a typical numerical simulation in which Neptune migrates outward by about 20%. You can see the ratio of mean motions or orbital periods between Pluto and Neptune starts off away from resonance, goes to exactly 1.5, and then is trapped. Initially, Pluto's semi-major axis doesn't change, but once it's trapped in the resonance, semi-major axis moves outward with Neptune. As the semi-major axis moves outward, the eccentricity goes up, and the inclination goes up as well due to overlap with an inclination resonance. What this means is that all of the funny features of Pluto's orbit, the high inclination, the high eccentricity, and the resonance are all automatically explained by the hypothesis that Neptune migrated. She also made a prediction, which is that because of this, if there were other objects outside Neptune, many of those would be captured as well. And so the existence, the fact of being in the resonance wouldn't be the peculiar thing that only happened to Neptune, only happened to Pluto, as it might have if it was some rare event, but that other objects would be in the resonance as well. That turned out to be correct. This is a plot of, as of Christmas Day, of the positions of all of the comets, asteroids, and Kuiper Belt objects in the solar system. There's Pluto. The red objects are Kuiper Belt objects, but all the white ones are Kuiper Belt objects that are also trapped in the 3-to-2 resonance. The strange azimuthal distribution just reflects the fact that some of the surveys had limited area, so that's where things got discovered. But you can see that the capture is something that happened to hundreds and thousands of objects, not just to Pluto. The idea of, I'm sorry?
What is plotted is the current position.
Yes.
So, Pluto is empty.
I'm sorry?
Pluto region is empty, except it's directly behind Pluto.
I guess that's true, yes.
The galactic plane. That empty region is the galactic plane.
Oh, yeah, I think that's right. This is probably the galactic plane where any sensible person avoids looking for Kuiper Belt objects. Okay, this view that the current architecture of the solar system has been shaped by planetesimal-driven migration has really seen a lot of activity in the last decade. as the result of publication of what's called the Nice model after the observatory in Nice. This is an elaborate model in which planetesimal-driven migration determines the entire architecture of the solar system. Basically, they start with a range of possible initial conditions, and then they try to find some initial conditions for the giant planets that after migration produces a system looking like the current solar system. They argue that not only does this model explain the current positions of the outer planets, it can explain the late heavy bombardment, the structure of the Kuiper belt, formation of irregular satellites of the giant planets, Trojan asteroids, the origin of Neptune's satellite Triton, et cetera, et cetera. You may or may not believe this model, but it's a nice indication of the ways in which planetesimal-driven migration may have affected many aspects of the solar system. The difficulty with planetesimal-driven migration, of course, is that the planetesimals only contain about 1% of the total mass that was in the protoplanetary disk. So any possible interaction with the protoplanetary gas disk is potentially much more effective at driving migration than interaction with planetesimals. And so if you think planetesimals may have been important, you really have to decide what happened with gravitational interactions between planets and the protoplanetary disk. I think that this was the mechanism by this could happen. The calculation of the gravitational torque between a protoplanetary disk and a planet was, I guess, first done by Peter Goldreich and me, although we were looking at a very different situation. We were looking at planetary rings. The conclusion we reached was that if you applied this to the solar system, you would conclude that Jupiter should migrate on a timescale of about 10 to the 4th years, very short compared to the expected lifetime of the disk. Of course, this was long before exoplanets were discovered, and so all you could sort of do at that point is shrug your shoulders and say, well, this is interesting, but I have no idea what to do next. Because this relies on differential gravitational torque, you can't tell, relies on an imperfect cancellation between the torques from inside the planet and outside, so you can't really tell what direction it's going to be. Bill Ward, in an extensive series of calculations, argued that normally you would expect, persuasively argued that normally you would expect the migration to be inward. And then after the first hot Jupiters were discovered, Lynn Bodenheimer and Richardson quickly recognized that this was a potential mechanism to move Jupiters from a plausible formation region out of the few astronomical units into the small semi-major axes where they were discovered. Since then, there's been a tremendous amount of work on the physics of migration. This is very nicely summarized in a recent review from the Protostars and Planets 6 meeting, and that's an article by Baruto et al. They go into much more of the detail of the physics than I will. What I'd like to do is try to give you a rough blackboard argument of how the migration works in its simplest form and how you calculate how effective it would be. So maybe we could lift the screen up, please. Thank you. Okay, so I'm going to look at what happens to a planet orbiting around the star on a circular orbit that has a disk inside it. Thank you. So here's the planet with a mass m sub p and some semi-major axis a sub p with the star way down here. So this is outwards. The planet is moving in this direction, but I'm working in the reference frame rotating with the planet. I'm going to imagine that it's got a disk on one side only that has some, disk has some surface density. So let's imagine what happens if a single mass element from the disk with some small mass m, because of differential rotation, it's going to go past the planet. Remember, we're working in the reference frame of the planet, so it's got a relative velocity of v, and because of the differential rotation in the disk, if this has a semi-major axis A, the differential velocity in the rotating frame actually will be 3/2 n times delta A, where delta A is AP minus A. We don't really care about the 3/2 because this is an order of magnitude argument anyway. So it travels past the planet with this impact parameter. That means it will feel a typical force, which is roughly g times the mass of the planet. At closest approach, that'll be roughly delta A squared. The length of time that it feels this force will be roughly delta A over the velocity, so roughly 1 over n. And if you use the impulse approximation, which isn't really correct, but it's good enough for an order of magnitude, it'll feel a perpendicular impulse, which is roughly f delta t, so g mass of the planet over n delta A. Sorry. Yeah, that's right. However, because we're working in this frame, the mass is stationary. That means that as the particle goes past, it doesn't just feel a kick delta v in the perpendicular direction. It has to conserve its energy. So the final velocity has to be the same. That means there has to be a backwards kick delta v parallel as well, so that kinetic energy is conserved. So v squared is v minus delta v parallel squared plus delta v perpendicular squared. We're interested in the limit where delta v is small, so we only have to keep the first order terms. That says 0 is minus 2v delta v parallel plus delta v perpendicular squared. So delta v parallel is delta v perpendicular. Sorry, this is v plus delta v parallel. Delta v parallel is minus. Sorry, I'm getting this. It depends on whether I want to make delta v. Clearly, because this is conserved, there's a change in the velocity back in the opposite direction to v. So I'll go back to making this minus, and then delta v parallel is a positive quantity over 2v.
I think there you either want 1 over v delta A or 1 over n without delta A squared.
I have this, yes, delta A squared. Okay, thank you. All right, so this says that the change in parallel direction is g times the mass of the planet squared over 2 n squared delta A to the 4th. And there's another factor of v, which is, hang on. This delta A to the 4th, there's another factor of v, which is n delta A. Doesn't look right? Yes.
So how come we're neglecting delta v parallel squared and not delta v perpendicular squared?
Because there is an extra term plus delta v parallel squared, but if I only look at the first order terms, the only consistent way to do that is to say delta v parallel is of order delta v perpendicular squared, so delta v parallel squared would be a higher order. Okay. Okay, so this, I'll drop the 2 GMP squared over n cubed delta A to the fifth. I should mention, by the way, that Ram already gave several different derivations of the Hill radius. If you want yet another one, the point where this perturbation stops to be being small, that is where delta V parallel is, or where delta V perpendicular is comparable to V, is also when this separation is the Hill radius. So that's the point at which this simple argument breaks down. So that's the change in parallel velocity. That means that there's a change in angular momentum of the particle, delta L, which is A delta V parallel, which is GMP squared over n cubed delta A to the fifth times A, and since this is going to be a real angular momentum, I'll multiply it by the mass of the particle. In fact, we have a disk, so let's imagine that I'm letting m represent the mass of the disk that goes past the body in some small interval delta A. That says that the mass is the surface density of the disk times the width. That gives a linear density, and then the rate at which stuff goes by is v delta t. So this is roughly sigma times n delta A times the small increment of A times delta t. That means that if I go here, the rate of change of angular momentum per unit time is g times the mass of the planet squared over n cubed delta A to the fifth, A times the surface density times n times delta A times the small element of semi-major axis that I'm considering. Well, rate of change of angular momentum with respect to time is a torque. That you can see that that's a negative torque on the disk, so it's a positive torque on the planet. So the torque on the planet is just equal and opposite to this. That n changes that to an n squared. Delta A changes that to the fourth. So GMP squared over n squared delta A to the fourth times sigma A dA. Okay, I can do a little better than that because the square of the mean motion is semi-major axis cubed over g times the mass of the star. So this is g mass of the planet squared or the mass of the star, A over delta A to the fourth times the surface density times the annulus that I'm considering. Now, in fact, we're not dealing with a narrow annulus. I'm going to assume, I've assumed that the disk is uniform, so let's assume that the disk, instead of looking at a small interval delta A, I'm going to look at the whole disk in this direction. That means I have to integrate this over delta A, so the total torque if I integrate this over delta A, then the number, I just take out one factor of delta A and get GMP squared over m star A to the fourth over delta A cubed times the surface density. That's the formula for migration. What this says is that the disk is exerting a positive torque on the planet. Similarly, if there was a disk outside, it would be exerting a negative torque on the planet. So the way to think of this is just that the disk and the planet repel each other. Any migration of the planet is determined by the difference in the torque between the inner and the outer disk, which depend on the surface density gradient and the temperature gradient. There's also a subtlety in here that I want to stress. Nothing I've said here has to do with the collective effects or the properties of the disk. So the first thing you might ask is, well, if this was just another planet, why doesn't one planet exert a torque on another planet? Well, we know that doesn't happen because the planets have gone around many billions of times since they started. But the reason for that is that this kick corresponds to giving a small eccentricity to the small particle. When it comes around again, one synodic period later, it'll get another kick, and that kick will have a particular relation in phase to the kick it got the last time. And so instead of continuing to grow the eccentricity will grow for a while and then decrease and go up and go down. So it'll induce a periodic oscillation in the eccentricity, which doesn't have any long-term effect on the orbit. However, in the case of a disk, let's suppose there's some viscosity in the disk. Long after this piece of the disk has gone past the planet, the interactions in the disk will damp out the eccentricity, damp out the perpendicular velocities, and when it comes back again, it will have forgotten that it saw this planet once before and experienced the same kick and the same change in angular momentum. Now, the nice thing about this is that I said, well, maybe the eccentricity damps out by viscosity, but maybe it's something else. Maybe this is a particle disk and the eccentricity damps out because of collisions. Maybe it's a gas disk with pressure and the eccentricity damps out because it excites, there are pressure waves in the disk that carry the excitation away. Maybe there's self-gravity in the disk and it's carried away by density waves. Maybe there's something else, magnetic fields, and it's carried away by Alfvén waves. The point is, you don't care. All of that action happens long after it's left the planet. So as long as there's some effect in the disk, whatever it is, that gets rid of this excitation before the mass element in the disk comes back again, the torque has to be exactly the same. So the effect is extremely robust and almost independent of the properties of the disk. This is an approximate calculation because I've used the impulse approximation, but you can do the linear calculation properly, and the only thing it does is add a factor of 2.51, 2.508. So apart from a factor of 2 or 3, the simple calculation works perfectly well. The time scale that you get out of this calculation, if you put in plausible numbers, is that the torque gives you a migration time, which is 1 over a dA dt minus 1 for the planet. And for plausible parameters, I can phrase this as 0.01 mass of the star over the surface density times AP squared. This is roughly the mass of the disk. So this is relative to a disk mass of 100th of a solar mass. It's m star times 0.001 over the mass of the planet. So this is corresponds to a Jupiter mass, and a minus the planet radius over, say, 10% of the radius to the third power. and the factor in front is 10 times the orbital period. So you can see that for plausible parameters, this is extremely rapid. This is an underestimate because it neglects the fact that there's a partially canceling torque from the other side. That maybe adds another factor of 10, but the number to compare this with is the likely lifetime of the disk, which is, for Jupiter, 10 to the 5th orbital periods, or a few times 10 to the 5th.
So this also explains the gap opening, right? The
Yes.
pulsation. And what determines the size of the gap? The Hill radius?
I'll say a little bit more about that, but the size of in contrast to the torque, which is almost independent of the physics, the size of the gap depends critically on the physics of what's going on in the disk. So you're right that if you have a disk here, the planet is pushing the disk away, but how effectively it pushes the disk away depends on the collective effects in the disk. So first it depends. The disk is trying to fill in any gap because of viscous spreading. But suppose that you make this excitation, and then over here, all the excitation is propagated away by sound waves. Then the angular momentum that you've put into the disk here doesn't, or the negative angular momentum that you put into the disk here doesn't stay. It gets propagated away and spread out over the whole disk. So it's very hard to open up a gap because it's easy for the stuff to fill back in. On the other hand, if you have a shock, which will tend to dissipate the angular momentum close to the edge of the disk, it's very easy to open up a gap. So the size of the gap that you open up is a reasonably complicated calculation, which depends on exactly what's going on in the disk. Okay, let me go back to the slides, please.
Also for the same arguments you just described, the minimal mass needed to open a gap.
Yes, right. Yes. Potentially extremely important. I'll say a little bit more about that. Just defer that. I'll say a little bit more about it later on. Okay, once the okay, I'll start with the side screens. The start of this is just repeating the formulas that I gave before. Again, these formulas give a migration time which is unrealistically short because they don't account for the partial cancellation of torques from inside and outside. Those typically lengthen the migration time, but by order the semi-major axis over the distance from the gap. In this context, with reasonable parameters for the gradients in the disk surface density and temperature, the planet usually migrates in. If there isn't any gap, the calculation fails. If you have a cold disk at the Hill radius, if you have a somewhat hotter disk, it fails at a distance which is roughly the disk thickness, and you have to do more careful calculations of what happens inside there. Okay, and the other two things I've said. In the case of a disk with pressure and relatively low viscosity, the eccentricity that you excite, as I indicated, is typically advected away by sound waves. The superposition of those sound waves gives a spiral wave propagating away from the planet. And you can see very easily in this case that the other way of looking at the torque is that this part of the wave, the inner part of the disk, is exerting a torque that's pulling the planet forward, adding angular momentum to the planet and taking it away from the disk. And similarly, the outer part of the disk is marked by a spiral wave that lags the planet and that's pulling the planet back and removing angular momentum from the planet.
Yellow is high density.
Yellow is high density, yes. Okay, so We know that the giant planets, despite Dave's reservations, it's likely that the giant planets acquired their gas envelopes while they were embedded in a gas disk, because that's the only place they can get the gas from. So that means they must have formed before the gaseous disk dispersed, so this process must have happened. The best estimates are for the minimum solar nebula with a thickness, with an aspect ratio of about 5%. The migration time is inversely proportional to the mass of the planet, and roughly at 1 AU, the ratio of the mass of the star to the mass of the planet. So for an Earth mass planet, this is maybe 3 times 10 to the 5th years, still shorter than the lifetime of the disk. For a Jupiter mass planet at 1 AU, it would be a few thousand years, which is very much shorter than the lifetime of the disk. So the good news about this is that, first of all, as I indicated, the torques, at least on the planets, that the exertion of that torque is an extremely robust process, which is independent of a lot of the details of the disk physics. And this provides a way to migrate planets into very small radii where they couldn't naturally form. The bad news is that it's a very robust process, which robustly predicts that all the planets in the disk should migrate into the star. So the primary prediction of disk migration is that there should be no planets. And much of the work that's gone on in the last 20 years is trying to retain the benefits of this without the defects of that particular aspect. There's been, as I said, a lot of work on the physics of migration, which I won't try to describe in great detail. The principal elaboration has been to recognize that the process that I described is a process based on linear theory. So it applies when the planet is small enough and the collective effects, sound waves or whatever in the disk are strong enough that the response of the disk is linear. There's also type 2 migration, in which, as you indicated, the repulsive force from the planet is sufficiently strong that the disk is pushed away from the planet and opens up a gap. Because the gap is present, the bigger the gap is, the more it reduces the torque, so it increases the migration time. And in the simplest case, where the planet is strong enough that it completely clears out the gap, since the gas can't go past the gap, the planet then migrates on the same time scale as the viscous evolution time scale of the disk as a whole. That may be an oversimplification. It can be that the clearing of the gap is imperfect and that gas migrates through the gap. That will change the relation between the migration time of the planet and the viscous evolution time of the gap, and that's just starting to be addressed by very high quality numerical simulations. The transition between type 1 and type 2, as we indicated, or as Ram mentioned, depends strongly on the physics of the disk. But for most of the reasonable estimates, it's somewhere between around 10 and 40 Earth masses.
Is it obvious that the gap width is smaller, is larger than its scale height of the disk?
No. That's why one of the reasons why these calculations are hard is that you really need to do 3D hydro simulations. And this is just a movie by Frederic Massey indicating a disk that starts in type 1 migration. The process gets stronger here and it transitions into type 2. You can see that that opens up a gap, and at that point the migration rate slows somewhat. And I just want to emphasize that we know that this process occurs because it occurs in Saturn's rings. This is a Cassini image of the very outer part of the rings. This is the outer edge of the rings. This is a gap that was discovered in the 19th century by a visual observer called the Keeler Gap. I think it's maybe 60 kilometers across. There's a small satellite in it, a few kilometers across. The ring material is moving this way relative to the moon on the inside, this way on the outside, and you can see that as it goes past, it excites waves, which are some combination of eccentricity variations and inclination variations, because the satellite orbit is not quite in the disk plane. You can show that this wavelength is just 3 pi times the distance from the satellite, and you can see that they gradually damp. Here you can see some evidence that they're propagating away from the ring edge. So the process definitely works.
Maybe it's worth mentioning that these are actually the cleanest system to study all this, because in most of these approximations you usually assume that the scale height is small.
Yes.
Any major axis compared to the distance from the planet.
Right. Here here the scale height is indeed very small. The distance, the gap width is many tens of kilometers, and the scale height is a few meters. It's also the cleanest system because you have spectacular data. We're getting some data, as Ruth indicated, from a variety of measurements of both debris disks like Fomalhaut and HL tau. There's some tendency, I think, whenever you see one of these edges or gaps, to say this must be, these must all be due to planets. But I think, as Ruth indicated, we should be very cautious about that interpretation. This is a disk that's only 10 to the 5th years old. This is out at 80 AU, and among other difficulties, it's pretty hard to see how you'd form a planet at that radius that quickly. Okay, for type 2 migration, if you use the same alpha model for the viscosity that Ruth introduced, to say the viscosity is some parameter less than unity times the square of the thickness of the disk times the mean motion, you can work out a formula for the evolution time. In this case, again, for standard parameters, 0.01 for alpha, distance of 1 AU, and a scale height of an aspect ratio of 0.05, the viscous evolution time is a few times 10 to the 4th years. Much longer than for type 1 migration, but still roughly a factor of 100 shorter than the lifetime of the disk. So it's very hard to get the migration time long enough that it won't move the planets by a large amount before the disk disperses. There are many additional complexities, which I'll mention briefly rather than describing in any detail. The parts of the disk within one Hill radius definitely do exert torques. These can't be in a disk with sufficient viscosity or high enough sound speed. Those are linear and they can be treated linearly, but more generally they're nonlinear. And one of the effects is that the disk elements can undergo horseshoe orbits where they gradually approach the planet and then are repelled and move back away in the other direction. That's another mechanism for angular momentum transport. There's a third kind of migration called type 3, which involves these horseshoe orbits. If you take the planet and you start it migrating, there's a self-sustaining feedback effect that means that if you start it migrating, this effect takes over and it migrates extremely fast, either in or out, depending on which way you started it. Turbulence, magnetic fields, the possibility that the planet orbit is eccentric or inclined, the question of dead zones where the viscosity in the disk may decrease dramatically because the MRI can't operate, because the disk isn't ionized except on the surface, what happens if you have additional planets, and so forth. These are all reviewed at great length in the Baruto et al. Article. I'm not going to try to discuss them in any detail. First, because they're mostly a little boring. Second, because some of these speed up the migration, some of them slow down the migration. But obviously, the critical question is whether you can slow down the migration by a couple of orders of magnitude. And most of these are, factor of 2 effects. Okay, so what are the problems with disk migration? The first problem, which has been around, since 1980, is why is Jupiter still here? If this is so great, why didn't Jupiter migrate into the sun? Now, there's an anthropic argument, right, which says that if it migrated into the sun, we wouldn't be here. But I'm not going to pursue that one. The most plausible argument emerges from the same people who brought you the Nice model. They argue that if you start the 4 giant planets in the gas disk at plausible radii and evolve them simultaneously under migration, they tend to get trapped in an elaborate series of resonances, 3-2 between Jupiter and Saturn, 3-2 between Saturn and Uranus, and so forth. And that once they're trapped in that resonance, the part of the disk outside Neptune is pushing it in, the part inside Jupiter is pushing it out, and it basically sits there and stops migrating. And that not only, according to them, preserves the planets from migrating into the star, but provides a natural starting point for the Nice model. This is called the grand tax scenario because Jupiter starts migrating in and then turns around and migrates out again and then stops. The second related but different problem is why are most of the giant planets at large orbital periods?
Scott, what about just opening the gap?
Because that's type 2 migration and
Can you have
the
the viscous evolution time of the disk as long as a million years?
you can you may be able to in the dead zone, and so that's a possible way. That's a possible way out of it. I agree. So, just to pursue that thought, this is the standard picture of the distribution of planets just from radial velocity surveys to minimize the selection effects. There's a large, as you can see, so the selection effects are what are removing the planets down here, but you can see that most of the radial velocity planets are detected at orbital periods longer than 100 days. That means that despite the selection effect that favors finding things at smaller periods, that means that whatever happened, most of the planets didn't migrate very much. Some of the planets migrated in here, but whatever process keeps them from migrating must have worked most of the time. So it has to be an effect that's extremely common. And most of the ways that have been thought of to stop migration are unlikely to work in most disks. So one of them is what are called migration traps, where due to a variety of gradients, the inward and outward migration cancels. Again, you can use, if they're a multi-planet system, the planets if the migration rates are different, they'll tend to converge. That'll tend to trap the planets in resonances. At that point, if the planets are close enough in resonance, they can clear out the material in between the planets. And then again, the disk is pushing one planet in, the other planet out, and it tends to halt the migration. This process definitely works, but again, like all of these processes, they seem to require enough special conditions that it's unlikely that they would be operating in the majority of planetary systems.
So let me disturb you again. What's the difference between these 2 planets that are sitting in a gap and clearly stuff between them and a single planet standing in a gap?
Well, the simplest answer is that when they do the numerical simulations, they move much more slowly. I believe the difference is that with the 2 planets in the gap, they can also adjust their relative separation in such a way to tend to cancel out the torques. But I actually don't know the answer for sure.
You have to migrate with the disk if the disk is frequent.
That's why one of the conditions is that the gas has to be able to leak through the gap. So this is one of the other things they have to be able to to manage.
Presumably it's not easier when there are 2 planets, or do they think it's easier? Because-
They believe it's easier when there's 2 planets.
Okay. So let me disturb you again. What's the difference between these 2 planets that are sitting in a gap and clearly stuff between them and a single planet standing in a gap?
Well, the simplest answer is that when they do the numerical simulations, they Okay. Closely related question, if they do migrate, why didn't they all migrate into the host star? This is a problem which became evident in the earliest population synthesis models, where they had to arbitrarily put a knob on the migration rate and reduce the torques by a factor of somewhere between 30 and 100 in order to reproduce the observations. One of the standard models is that maybe the disk is truncated, maybe by the magnetosphere of the star, so the migration stops well outside the star. The other possibility is what used to be called the last of the Mohicans scenario, where lots of planets migrated into the star, and what we're seeing is just a small fraction that happened to be on their way to migrate when the disk dispersed, and then they got stranded on their way into the star. The difficulty with that is that it requires extreme fine-tuning. If the migration time is 1% of the disk dispersal time, you'd expect only 1% of the planets to be stranded in this process. So it really seems difficult to have this operating in a lot of systems. Again, maybe you can do it with multi-planet systems, or maybe there's just some aspect of the migration physics that not only do we not understand, but that where we're off by a couple orders of magnitude.
In this scenario, when the planets just agree that on the whole star, how massive this has to be in order to produce those planets?
Absolutely. And do they pollute the stars too much? All of these are reasonable concerns. I think this was a model which was popular when our knowledge of the demography of the planets was a lot less good, and where we didn't know that they were so common. Let me just point out about one of those mechanisms. If the idea is that there's an inner cavity that stops migration, then you'd expect the planets would all migrate into the edge of this cavity, to the inner edge of the disk, and then stop. So you'd expect to see a pileup of planets at very small radii. But in fact, you don't. This is a log plot, and you can see that the number density of comets per unit log period is more or less constant over about 1.5 orders of magnitude from in here out to the point where you start to get a pileup. And again, it's very hard to explain that if there's any process where planets migrate in quickly and then stop. I should also mention, we've heard a lot of talk about hot Jupiters, which is basically the planets in this region here. But you should beware about calling things hot Jupiters, because there's clearly no separate population of hot Jupiters. There's a continuum ranging from hot Jupiters to warm Jupiters to cold Jupiters, and there's nothing special about the hot Jupiters. Another problem, where did the eccentricities come from? One of the strong features of the planets discovered by radial velocity surveys is there's a wide range of eccentricities. The range is going down here a little, but that's mostly because things at very small semi-major axes and high orbital eccentricities tend to be tidally damped or collide with the star. In most cases, migration, the gravitational interactions with the gas disk tend to damp the eccentricities. There are some cases where they can be excited, as was pointed out by Ram some time ago. If the planet opens a gap, if the eccentricity exceeds some threshold already, and if the radial excursions from the eccentricity are small enough that it doesn't crash into the sides of the gap. Recent simulations by Duffel and McFadden have confirmed these analytic arguments. Nevertheless, there are enough conditions here that it seems unlikely that this is generally, that for most planets, the migration excites the eccentricities. Now, you might argue that the planets get their eccentricities damped, then they migrate in, and then gravitational scattering between the planets at small semi-major axes excites the eccentricities. But that doesn't work either, because for hot Jupiters, the orbital speeds are so high compared to the escape speeds that when you have gravitational scattering, the planets tend to collide rather than having their eccentricities excited. We've also heard from Dave that about half of the hot Jupiters have large obliquities, large angles between their spin axis and the spin axis of the star and the orbital angular momentum axis of the planet. This is one of the standard plots showing the range of obliquities as a function of distance. There are many ways to produce the high obliquities. It could include, occasional collisions of planets with the host star, reorientation of the disk, protoplanetary disk due to external torques, magnetic fields, a variety of mechanisms. Nevertheless, in the alternative to disk migration, which is high eccentricity migration, which you'll hear about, I think, on Monday, the high obliquities arise naturally. In disk migration, you need some separate process and some separate hypothesis to explain why everything isn't aligned. Resonances. I argued yesterday that convergent migration from small eccentricities inevitably produces capture into resonance pairs. This is a plot from the planets that are confirmed, that is, that have reasonable masses. It does show an enhancement at the 2-to-1 resonance and the 3-to-2 resonance, although you should be a little cautious about this because this particular plot includes planets with masses coming from TTVs, and those are biased towards being resonant. The optimists or the enthusiasts about migration would argue that this is the smoking gun that shows that migration has occurred. On the other hand, as we've also heard, the Kepler planets show really almost no indication for preference for resonances. In fact, a gap at the 2-to-1 rather than an enhancement. So you have to explain why the expectation from migration that the Kepler planets would show very strong concentration at resonance didn't actually occur.
I asked this question in Greece, and they was figure out the angular answer that they basically all the resonances were effectively destroyed afterward by planet-planet interaction.
There are
Sorry, when this dissipated, all resonances were effectively destroyed.
for every point I've made, there are lots of explanations. Nevertheless, eventually you would expect the disk migration theory would correctly explain something without having to backtrack and come up with a new effect after the observation comes out. So yeah, these are it could be the migration time is extremely short. There could be turbulence in the disk or some other process that makes the planets jump over the resonances, or it could be that the Kepler planets didn't migrate. Again, there are certainly ways out of all of these. Okay, so let me summarize what I think the current status of planetary migration is. I think we do have progress and real problems. The planetary migration due to gravitational torques from the planetary disks is natural. It's an inevitable process. It's very hard to make it go away and very hard to make the time scale as long as you would like. If you apply the standard models, most of the planets should migrate inward in a time much shorter than the dispersal time of the disk, and therefore the natural expectation would be that they should fall into the star. A lot of more sophisticated models have been made. They've identified a lot of new effects, including type 2 migration, type 3 migration, the effect of co-rotation, and so forth. They indicate that the migration time and the direction can depend on a lot of gradients and properties of the disk. They can depend on the presence of other planets, and so forth and so on. Some of these changes make the migration faster, some of them make it slower. But I think there is no effect that's been discussed yet that will make the migration time for most planets and most protoplanetary disks longer than the disk dispersal time. In addition to that, a simple version of my next point is that every prediction that's been made from disk migration has proved to be wrong. Exoplanets are a subject area where observational progress has been really quick. when the first hot Jupiters were discovered, the disk migration theorists said, oh, this is because there's an inner edge to the disk, therefore we're predicting that all of the planets should be there should be a lot of hot Jupiters and nothing outside that. That turned out to be wrong. Later on, they said disk migration causes planets to be captured in resonances, so all the Kepler planets should be in resonances. That turned out to be wrong. Every time you've made a prediction from your current understanding of disk migration, it's turned out to be wrong. So it would be very nice to have an alternative to disk migration, but I want to stress this requires two things. The first is to show that the standard migration times are too short by several orders of magnitude. That is to show that disk migration doesn't move all the planets into the star, leaving us with no planets. And once you do that, you second have to find an alternative migration mechanism because you're still stuck with the problem of producing the hot Jupiters. And I think this is, one of the really serious problems with our current understanding of planet formation. Now that was all I wanted to say on migration. I had a couple of other brief topics, but let me first ask if there are any questions.
There's something I don't understand about the migration model. What you're saying is that the distance between you and the star is pulling you towards the star. And the inevitable consequences is that it's going to spiral in. But the matter outside is pulling you outwards. So it seems more natural that there's going to be some point where it settles and there's an equilibrium between the two forces.
So first of all, the material outside is pushing you in. Material inside is pushing you out. As the disk, if it's in type 1 migration, which is in which you don't open up a gap, as long as the gradient in the disk looks reasonable, it will continue to push you in. Once you get close to the inner edge of the disk, most of the material is outside you, and so it pushes you in even more strongly. In the case of extreme type 2 migration, where there's no gap, where you've got a complete gap and there's no gas crossing the gap, then if there's no migration, eventually the inner disk drains into the star through viscosity, and then there's only material outside you, and that pushes you in. So in both cases, it's very hard to stop the migration because in the end, most of the material in the disk is outside you and pushing you in. Okay, let me just comment briefly on a couple of other subjects that came up earlier or didn't come up earlier in my earlier talks and I didn't have a chance to discuss. I spent a lot of time talking about numerical methods, but I didn't talk about any of the results. And the most important result from the numerical methods is trying to understand the very long-term stability of multi-planet systems. That is, if you build a system like the solar system or one of the exoplanet systems, can it survive for 10 billion years? And so what you would like is, so there's two ways to do this. One is every time you get a new exoplanet system, you do a 10 billion year integration and see what happens. But you'd like to develop some empirical criteria. The best criterion we have is again based on the Hill radius, the ratio of the mass of the planet to the mass of the star to the 1/3 times the semi-major axis. The experiments that have been done with numerical integrations say that if you have a multi-planet system with two planets, masses m and m prime, semi-major axes a and a prime, eccentricities e and e prime, and you want it to be stable for some number of orbital periods, the simplest criterion is that the point of closest approach between the planets has to exceed a certain number of Hill radii. So the criterion is that the pericenter of the outer planet minus the apicenter of the inner planet has to be bigger than some dimensionless number times the mutual Hill radius, where you just replace the mass by the sum of the masses. And the typical number to keep in mind is that if you'd like to be stable for 10 to the 10th orbits, you need a dimensionless number of about 10. No, because Pluto's stuck in the resonance. So you can certainly make special configurations like the Pluto configuration that are stable even if the orbits are crossing.
Pluto has a negative spin.
Right.
But Scott, let me ask you about this. For two planets on circular orbit, I think we are turning 2/7 rather than 1/3. Is wisdom thing for
There are two natural measures of the characteristic sphere of influence. Well, there's three natural measures of the characteristic sphere of influence of a planet. The Hill radius, which is 1/3, and technically that's, say, the distance to the Lagrange points of the planet. There's the wisdom criterion, which is like this but with a 2/7. That's the criterion at which the perturbations are sufficiently strong that the orbit of a passing test star becomes chaotic. For the numerical simulations, 1/3 is 0.333, 2/7 is 0.2857 or something. You can't really distinguish them.
If you go to small masses, you will distinguish.
If you go to extremely small masses, you could distinguish them and you could tell which one was better. With the current simulations, you can't really tell, so if you change that to 2/7, I don't think it would make much difference. There's a third one, which is 2/5, I think, which people use when they're doing spacecraft trajectories, but let's not worry about that one. Neither did I, it seems. I'm just telling you, that's... Okay, so this is a recent summary by Yen-Chin Wu of the results. So this is a variety of people who have done the simulations. This is their estimates of the critical separation. You can see that they don't agree perfectly. You wouldn't expect to have this to be a perfect correlation. But again, roughly speaking, what you should keep in mind is that if this separation is less than about 10, you're going to have a hard time making your system stable for a reasonable lifetime. So this is somewhat useful, but I'd like, the thing that always seems to me to be really striking about this is that at the moment, this is the best empirical method that we've got. It may be pretty lousy and pretty simple, but it's the best thing we've got. And apart from this, if you want to decide whether a system is stable, there is no alternative other than integrating the whole thing for 10 billion orbits. So stability determination is difficult and appears to depend sensitively on the details of what's happening, and this is all you've got if you want to determine stability. I also wanted to make one brief comment on the accuracy of long-term orbit integrations. One of the questions that was raised in the last talk, questions that were raised included questions about round-off error and the question about how you whether you should believe these very long integrations. I just wanted to draw your attention to a paper by Wayne Hayes, who's actually a computer scientist who got interested in this problem. He integrated the solar system and the 4 giant planets for 200 million years. The comparison of he used 3 different integrators. The comparison of the different integrators is difficult because the solar system is weakly chaotic. If any small change diverges exponentially with an e-folding time or Lyapunov time of 13 million years. So instead of comparing how close 2 different integrators are and expecting that they'll stay close, all you can really do is see whether you reproduce this exponential divergence. So what are shown here are 3 methods. One is the Winston-Holman symplectic integrator that I described before with a time step of 4 days. One is a very high quality non-symplectic integrator. It's a method called the Cowell-Sturmer method. It's 14th order. So it's going to very high order to compensate for not being symplectic. That had a time step of 4 days. The third one is a really remarkable method. It's a Taylor series method. What the package does, it's a package called Taylor 1.4. is it expands the equations of motion in the Taylor series, which you can do for Newton's equation, although not for all systems. And then it automatically calculates the optimum order for the Taylor series as a balance between longer time step and more algebraic complexity. And in this case, it decided by doing the computer algebra that the optimum order was 27, and the optimum time step was 220 days, a factor of 50 longer than the other integrators. And you can see that all of the methods are giving the same exponential divergence, the same Lyapunov time, and roughly the same amplitude. The rule of round-off error is that, as I said, small changes in trajectories make them diverge. If you have a shorter word length, you have more round-off. That introduces bigger changes in the orbit. And so it sort of seeds the exponential divergence more quickly. So when he went to 80-bit precision from 53-bit precision, you got the same exponential divergence, but a lower amplitude. I think these are the most careful estimates of the effects of numerical methods, and I think they're very reassuring that the numerical methods are actually capturing the physics of what's going on in these long integrations. I finally just wanted to say a few words about one of the other gravitational interactions between planets and protoplanetary disks. As I've said, whenever you see a structure in a debris disk or a protoplanetary disk, there's a tendency to ascribe it to an unseen planet. And I'd just like to stress briefly that that's not necessarily the only possible explanation. We know that disks can support density waves. This has been recognized since very early work by Safronoff and has been popularized by people trying to explain spiral structure in galaxies. Safronoff pointed out that in the limit of a low mass disk, you could use a WKB approximation to approximate the dispersion relation of density waves in disks. The Safronoff dispersion relation involves the azimuthal wave number, the angular speed of the disk, the pattern speed of the pattern, the epicycle frequency, which is basically the difference between the mean motion and the periapse precession rate, surface density, and radial wave number. Typically, this means that if you have a low mass disk and a thin disk, because the surface density is low and the sound speed is low compared to these other terms, the wave number has to be big. That is, you have a very tightly wound density wave, which is not something you could see in general in a protoplanetary disk with current resolution. However, because Kepler disks have the particular property that the epicycle frequency is almost the same as the orbital frequency, if you restrict yourself to waves with m equals 1, that is lopsided one-armed spirals, and to situations in which the precession rate is small, if you expand out this expression, you find that the zero-order terms cancel. There's a set of first and second-order terms. The second-order terms are so small that you can drop them, and you end up with a dispersion relation, which is somewhat simpler, and which says that you can have large-scale density waves, that is, waves in which the azimuthal wave number is comparable to 1 over the radius, so long as the pattern speed is small. So what this says is that in a mathematical sense, you can make the surface density as small as you want. You can make the sound speed as small as you want. And as long as the precession rate and the pattern speed are small, you can still get a large-scale density wave. And these could be excited by passing stars, spontaneous instabilities, or a wide variety of other effects, and don't require planets. I did calculations with Amr Jalali of what these density waves looked like. This is a sample for a typical disk. So they're clearly there, and they clearly do resemble some of the patterns that you see in some protoplanetary and debris disks. And finally, I'd just like to point out that there is actually a very simple way of distinguishing in principle whether asymmetries that you see in the disk have to do with this kind of density wave or with a planet. If they're due to a planet, the planet is orbiting around at its Keplerian motion, and the pattern will be orbiting around with it. In these cases, because the pattern speed is small, the pattern should be essentially stationary. The resolution we have with debris disks and with ALMA, typically you can expect that in 10 to 20 years you should be able to see the angular speed of any asymmetries that you look at. And so over an extended period into the future, I think there is a straightforward astrometric test that will distinguish density waves from patterns induced by a planet. Okay, let me stop there.
Questions?
I think this is kind of open-ended, but, and maybe just reiterating what you had already said, that it just seems to me, you know, we have systems that end up like our solar systems, and other systems that seem to have ended up in the multi-planet without one planet at close separation. And then we have another class of systems that does end up with essentially one planet at a close separation. So maybe this is a philosophical question, but it seems that no matter what mechanism you come up with to produce one system will not produce the other, and vice versa.
Well, maybe, I don't know. I hope it's not philosophical. That is, I hope that with enough data, you would be able to see a natural split into these two kinds of systems, if that hypothesis is correct. Well, I've discussed this with Dave already, but what concerns me a little is that planet formation is obviously an extremely messy process. And instead of simple principles emerging, we seem to be in a situation where as the data gets, we learn something, we make a model for it. We learn some more, we find out the model doesn't work. We elaborate the model some more and we can fit the data. And eventually we're going to run out of data. We'll have a model that fits anything, but will we have understood what's going on or not?
That will be a good topic for future discussion, and we will. Are there other questions? Okay, thanks, Scott.
Thank you.